All right, so after this recap, we now really move on to the tree generalization of shortest path. So after this recap, you know what I mean when I draw a picture like this, a factor graph. I've here given a small concrete example with just 2 discrete states per node, because I'm lazy, I didn't want to draw so much. And I've highlighted one particular shortest path from S to T, and I didn't give any edge weights, so I simply pretend that what I've highlighted here in green is indeed the shortest path. All right, so this was an open chain. Now let's assume that for one of the reasons that I gave you in the introduction, where we do need a tree, that we have a structure like this. Yeah, so I'm now generalizing my graph. This node here with its 2 states I represent there. Just by the way, in all of these examples here, well, it so happened that all nodes had the same number of states, or all variables could take the same number of states, but that need not necessarily be so. Yeah? So it would be fine to let this one have 5 states and the one on the left and the right to have 2 states, as long as we have this directed acyclic graph. The Viterbi algorithm still works. Of course, when you do have a perfect trellis, same number of states in each variable, you can make things a little bit more efficient still in the implementation. All right, so let's say now I'm looking for the shortest path from S to T prime, and I'm looking for the shortest path from S to T double prime, and maybe I'm lucky, so maybe the shortest path, I wanted to have the highlighter here, so maybe the shortest path continues here. And why do I say lucky? Because the green shortest path and this blue shortest path here, well, I mean, for sure, we know that they must agree here, because if there was a shorter path, for the green one, an even shorter one than this one, then the blue one would also follow it on the left. Yeah? So it's, I mean, they must agree here, but as we have no guarantee that they do agree there. So here agree means that both these shortest paths, they happen to go through the same state, or to select the same state for this variable here, but it need not be so. Yeah, so here I have an example where the shortest path from S to T prime is the green thing, shortest path from S to T prime prime is that thing. And you see that they now select different states in this variable. And now you can ask, well, what shall it be? Upper state or lower state, but not both at the same time. So what can we do about it? I'm halting the recording. So what we can do is we can try and this extra side branch, we can try and agglomerate all the costs associated with the side branch and incorporate them in the costs that the shortest path on the main branch will need to pay. So here I wrote, let's minimize over the side branch and update the cost of the branching point states. So in my picture, I normally have costs only for these pairwise potentials. You see, I have only these pairwise factors here. I could add explicitly these unary factors. So I could say that there is a particular cost associated with each state that these variables here can take. And as I argued earlier, normally these unary costs are not shown explicitly because they can be absorbed in the pairwise costs. But now let's represent them explicitly. And then I can ask, what's the cheapest way of somehow catering for that side branch? And this cheapest possible cost of catering for the side branch, starting from each possible state, the upper state or the lower state, these extra costs, I can add them to this unary, if you like. And they will then impact the choice of path on the main branch. That's the basic idea. Now there's a question, well, what is the main branch and what is the side branch? So the argument works for any number of side branches, and it works for any choice of main branch. Now we only need to do the bookkeeping correctly, but what we do call main branch and what we call side branch is completely arbitrary. All right, this was qualitatively in pictures. Now let's do this in formula. First, we go back to the chain model. Yeah? So we go back to our chain where I have variables, pairwise factors, variables, pairwise factors, and so on. We revisit this case. So earlier here, to stress that we've absorbed the unary costs in the pairwise, I put a tilde here. So we want to minimize this energy given by the sum of pairwise costs. And this minimization here is over all variables. Now, this minimum operation here, it distributes. So in particular, if I want to minimize over Z1, I don't need to take these factors into account because they don't have Z1 in the argument at all. So I can push in, if you like. So I can write I can rewrite this. I can say I want to minimize over Zn, and I want to minimize over Zn minus 1, and so on. And I want to minimize over Z1. This is always true, just a different way of writing the minimum over many different states. Now the next equality is only true for this particular objective function here, where I can push the minimization over Z1 in, so that it acts only on those parts of the objective function that depend on Z1. So I've pushed it in all the way to here, and I have now a minimum over the pairwise potential depending on Z1 and Z2. And you can think of this pairwise potential as a table. So this psi 1, 2. Remember that Z1 could be in different states. This could be in the state, I'm going to number the states here, or I'm going to give them letters. This could be in state A, or B, or C, or D. And my variable Z2 could be in state A, or B, or C, or D. And we now have a cost for each of these. For example, a smoothness prior would say, okay, if we transition from A to A, the penalty is nothing. So we have zeros on this diagonal, and perhaps we could say, all right, we have a penalty of 1 off the diagonal, and then we want perhaps a quadratic penalty. So let's say we have a penalty of 4 here, and then if the transition is bigger than, or if the state difference is even bigger, we're not going to penalize this any harder. So I'm just going to leave it as at 4. So for example, that's the kind of table that we have. And if we now ask what is the lowest cost here in this table if I minimize over one of the states. Actually, this table here is uninformative, but as soon as I add unaries, I will start to see a difference between different states. So, for example, I could say that a unary table here would be I'm making up these numbers now. Yeah, this would be the cost of psi1 associated with states A, B, C, D. And so now we do have a preference, namely state A here is the cheapest one. And in this case, if I have minimized over my over the states of variable z1, I am left with, well, the cost for, I have a function that's now a function of z2 only. And this is why I write here that this is a function. I'm writing m for message, which only depends on z2. It no longer depends on z1. I've not integrated out z1, I've minimized out z1. And well, this is the message, if you like, from random variable or from variable 1 to variable 2. So this is why I wrote m1 arrow 2, message from 1 to 2, and its value depends on, well, now the possible states of variable 2. Okay, so we have a function depending on z2, and we have a pairwise potential depending on z2 and z3. And these two functions are now the only ones that depend on z2. So I'm performing the minimization only, the minimization over z2. I'm performing this minimization only over these two. And then you iterate this argument. So I've minimized only what depends on z1 over z1. I'm minimizing only what depends on z2 over z2, and so on. So I'm sending messages consecutively from the beginning to the end of the chain. So this is just Viterbi's algorithm rewritten. All right? And now, well, when we have side branches, we're going, where's the camera? We're going to send the same message, and where these branches meet, we have to add them up, and then we will send them onwards. And this is done in a technique called message passing or belief propagation. So you start by drawing your vector graph. You pick an arbitrary root node, or maybe it would be more in line with what I've called this previously. If I say we're picking an arbitrary terminal t, and now we start sending messages from all leaves. And well, the way I had depicted these chains so far, we had always started with a variable. So we would send a message from a variable to the closest factor. And if it has no unary associated with it, well, then the message will be 0. But sometimes a variable has a unary associated with it, like a preference to be in one given state. And then the first message is, well, just the value or the cost of being in any of those states. So this is the boundary conditions. These are the first messages that are sent from the leaves towards the root. And now comes, I've copied this from old lecture slides when I had not yet tried so hard with my handwriting. So I'm going to read this to you. And then send messages asynchronously in the order in which their arguments can be evaluated. So, what does that mean? We send a message, for example, here, but now the message from this factor towards the root, this message here, can only be sent when or once it has received its input. So it's waiting until it has received its input, then it's sending it along. Now this variable here cannot send its message further towards the root because it's missing input from the other side branch. So this has to happen first. And now this factor here has all the input it needs. It can now combine these messages and send them onwards. This one cannot yet send to the root because it has to wait. Now it is in a position to send an informed belief, and this one is also sending, and then we're done. Now, if you don't want to, randomly send messages and then block nodes until they have finally received all their input, you can, as a pre-processing step, you can measure the distance from the root. And this is what I did by these green lines. Yeah? So here is the root, and then these are the factors at a distance of 1 from the root. And then the next equicontour was for everything that's a distance of 2 from the root. And then there's everything that's at a distance of 3 from the root, everything that's a distance at 4 from the root. By the way, you see that alternating here in a factor graph, we always have variables or factors. So at these even distance, or let's say at the odd distances, at a distance of 1, 3, 5, I only have factors. And at a distance of 2, 4, 6, I only have variables. In other words, a factor graph is a bipartite graph, where on the one hand I have factors, on the other hand I have the variables, and I have edges only between factors and variables, but not between variables and variables or factors and factors. But that's just a side remark. Good. So let's maybe start here at the bottom. We are looking at a message that my random variable zs, here this is random variable zs, which it is sending to factor psi t. Yeah, and so I made an arrow here to say that this is the direction in which we're sending our message. And well, this message, this is a vector. If zs has different possible states, then what this message says is, what is the sum of the smallest possible paths from all the side branches that meet at zs? What's the sum of the minimal costs to end up in a given state in zs? And if zs has capital K possible states, then this is a vector with 1 times k entries. All right, and well, these costs, how are they accumulated? They are simply being added up. Yeah? So the important thing is that we have a summation here. Let's look at what is being summed over. Let's look at this notation here. We sum over all the messages from neighboring factors psi I towards variable zs. Yes, on the right-hand side, these three here, these are these factors psi I, and what we say down here is we're summing over all factors psi I in the neighborhood. So script n here says in the neighborhood of a variable zs. This should be a z, excuse me. We're summing over all factors that are connected to variable zs, except we're not summing over factor psi t because we don't have any information from it yet. That's where we want to send information to. Okay, so this is what's happening at the bottom. We are summing up the minimal costs of reaching a particular state from all the side branches. All right, and now we send a message from a variable to a factor. And now in the upper equation, we're sending a message from a factor to a variable. And this is now where this minimization is needed. So if we go back to last time, let's look at this here. We were looking at a particular node, let's say this state here, and there are various ways of reaching it. We can reach it via here, or okay, like last time, I'm being lazy, excuse me, I'm picking the node which has no unary costs associated with it. All right, and we have various ways of reaching it. Namely, we can reach it like so, or like so, and there's no other way of reaching it because there are no other edges coming into this node. Now, one possible cost is 4.3 plus 2. That's a total cost of 6.3. Or I can reach it via 6.4 plus 0. That's a total cost of 6.4. Or I can reach it via 2.3 plus 2 for a total cost of 4.3. That's the winner. Yeah, so I've taken the minimum over this, and this incoming path. I've taken the minimum over them, and I found that this was the winning path, the one down here. So there was this minimization operation. And now we have the very same thing. We have the minimization operation, except that this time, well, we have many possible incoming states. This here is a factor which is not a pairwise factor, the ones that we have looked at so far, but you see that this is a higher order factor. In this case, we have a fourth order factor, which here depends on 4 variables altogether. And we take the minimum of these incoming messages and then the potential associated with this particular factor. Yeah, so remember the minimum operation, here it is again. All right, So, you know, this here is the core message of today. Everything before was motivation of where is needed in computer vision, and recapitulation, things that we have done last time, put in a slightly different picture or put in, you know, written in a different way. So this is the main, the hard content of today. And in the rest of the lecture, we will then look at various ways of using this in computer vision. But before we go there, a few comments. Message passing, this is what this technique is called, it gives us the exact map solution, I would say what this is, on tree-shaped graphical models. So map means maximum a posteriori, and why? Well, because in terms of Bayes' theorem, we are interested in what is the most likely state given some observations. If we have a likelihood, the probability of observations given the states times a prior over the states divided by the evidence. So this is Bayes' theorem here. And now, oftentimes, this, or in undirected graphical models, we are writing this probability here as e to the minus some energy, an energy of associating, or let's call it a likelihood of observing, of making certain observations O given states Z. And this energy itself often decomposes into sum over, for example, pairwise potentials. So I'm writing here sum over I, sum over J, psi ij of Ci Cj. And similarly, we may have here for the prior, we may have a product over well, unary priors, or priors for one variable that are independent of the others. So I could write this as a product over priors of single variables, or I can write this similarly in terms of a summation, over unary potentials here. All right, and if we now, and the aim here is to find the argmax, so to find the most likely state. And if we now take the logarithm of this, and we lose, you know, this e to the power of, and we're left with this energy minimization problem. So we can say that the argmax of this is going to be the same as the argmin of the kind of energy that we've written before of Z condition on O, except that previously I did not condition explicitly on O. I just wrote energy depending on Z. All right, and this solution here, so this argmin, let me call it Z star or Z optimal or whatever you want. This is called the maximum a posteriori solution, or in short, map solution. Now, you don't need to know these equations here. I'm just trying to tell you where this name comes from, or what's meant here when I say that message passing gives the exact map solution on tree-shaped graphical models. Now, the emphasis here is on tree-shaped graphical models. And yes, they're very versatile, we can do many things with these, but we cannot do everything we want. So sometimes, importantly in computer vision, sometimes you want to model each and every pixel, for example, as a variable. And if I model each and every pixel as a variable, well, I obtain something like this. And let's now this was just 4 pixels. So if we continue this, now not exactly a tree, anything but a tree. So we have lots of loops here. So what do we do if a graphical model is not tree-shaped? Okay, there are many choices, and that's material for a lecture, not one lecture, but a whole semester course in itself. 2 semesters. But basic strategies relating to what we're discussing today are the following. So one strategy is to, well, if it is not a tree, let's turn the graphical model into a tree. So for example, here we have something which mainly looks like a chain. I'm making it a bit longer to emphasize it. It's mainly a chain, except that at one point we have this tiny loop. So, well, one possibility is to, as indicated here by this red or this blue circle, I'm going to take these here and I'm going to turn them into a fat node. I'm making a super node out of these. And the super node, you see, it's the blue thing here. I've put it there, and the remainder now is just a chain. So I can again use Viterbi, or I can use again message passing. Now, the limitation of this is, well, that it is a fat node, so it will have many states. In particular, if this node here, let's say there are 3 nodes, each of them had 2 states, so then the fat node will have 2 times 2 times 2. It will have 8 states, and correspondingly, these tables here, if I now want to specify what this psi will look like, well, if this guy here has 2 states and this guy here has 8 states, then this is going to be a 2 times 8 table, not a 2 times 2 table as you would normally expect. So we can still do Viterbi, but at the cost of having a much larger number of states to deal with. And this is called the junction tree algorithm, and it works well for graphs of so-called small tree width. I'm not going to define tree width now, but qualitatively, if you squint, if you look from a distance and it looks like a tree, almost, then that has a low tree width. This thing here, the Cartesian lattice, never looks like a tree, so this has a huge tree width, and you wouldn't want to use a junction tree algorithm here. Another possibility, earlier, up here, I have always been insisting that, well, we need to wait for all incoming messages before we can send our outgoing message. Now, if the graph has loops, we can cheat. If an incoming message is not coming in, we can just invent one and pretend that we had received it for a fact, and we send our outgoing message anyways. And if we iterate this, so what I've written here is invent missing messages, iterate, and hope for the best. Then this is called loopy belief propagation, and it will give us an approximate solution in general. And the third approach, how to use tree ideas when your graph is not a tree, is to use dual decomposition. So here in this example, we have a Cartesian lattice, and I have now drawn a red tree, and I have drawn a blue tree. Both of them are sort of half the truth. Yeah? So the red tree spans the columns plus the bottom. The blue tree spans the rows plus the rightmost column. We can do exact optimization or exact inference on both of these, and we will get different answers. Well, and we can then start shifting around potentials between these two trees until we reach a consensus answer. This is an approach called dual decomposition, which also gives us an approximate solution. All right. Now we've earned a lengthy break. I want to use 10 minutes and give you some time to digest all this. Well, lengthy break. I mean, 10 minutes was not long in normal times. Let's have a 10-minute break here. You can stare at this, and we can have questions afterwards. And after that, we will talk about so how to use this in modeling computer vision problems.